Welcome back to Basic Electronics video lecture. Now from this video onwards we will study the data converters. So in this data converters we are studying the DAC, digital to analog converters, and ADC, analog to digital converters. Now before that, why we need this ADC and DAC? So now naturally generated all signals are analog signals. Now if we wanted to control any device, so nowadays if you see, all controlling devices are the digital devices. So now if this is my microprocessor or microcontroller, if this is my microprocessor or microcontroller, so microprocessor and microcontroller can only take the digital signals. Now it accepts the digital signal and it do some process and gives the digital output. It will take the digital input. Now this is nothing but a digital input, and it will give the digital output. But all naturally generated signals are what? All are analog signals. If I wanted to control or if I wanted to do the manipulation, then if I wanted to give those signals to the microprocessor or microcontroller, then it will not accept the analog signal directly. So for that we need one analog to digital converter, ADC. Now here we need to give the analog signal or analog input, and it will convert the digital, and those digital signals we are applying to the microprocessor or microcontroller, and it will do some process, and again it will give the digital output. But again, if few applications we can run only on the analog inputs, so that time we need the DAC, digital to analog converter. These digital signals we are applying to the digital to analog, and it will generate the analog signal. Now for example, speaker is there. Speaker we can run by using only analog signal. If any digital input is there, that will be again, that should be converted into the analog. Now motor is there. So motor is a analog device. So when we give the signal, then stepper motor it can take the digital signal. But if we take normal motor, then it need analog signal. So now fan is there, again it need analog signal. So after doing some process, it will generate the digital. Again that digital signal should be converted into analog to run our application. For that again we need the DAC. That's why now in this Unit 5, second half, we are going to study the analog to digital and digital to analog converters. In that, we in the syllabus, R to R DAC is given. So another DACs are also there, but only R to R is mentioned. R to R ladder DAC is mentioned. Now, which is going to convert the digital input into the analog output. So now here we are giving the digital input, so it will convert into the analog. So how it is going to do that we will see here. Now this is the operational amplifier, so which we already studied in the unit 4. So it is having the two inputs. For negative input I am applying the digital data, and positive I have given the ground. So this is the input resistor and this is the feedback resistor. I am taking, this is 2R and this is R. This is the inverting amplifier. Now what is inverting amplifier output? It is nothing but what? Minus RF. This is RF is nothing but what? Feedback resistor. Minus 2R divided by R into V in. Whatever the voltage we apply here, it will multiply. So output is equal to gain of this. Gain is nothing but what? Feedback resistor by input resistor. So this is the gain. But here we are applying at the input. Now I am taking the 3-bit DAC. 3-bit DAC means what? 3 binary bits I will apply. Equivalent analog voltage we are going to calculate by using this circuit. Now how to apply? Using R to R. Means what? We are using the R and 2R resistor. Now here I am taking 1 2R, and this is the R, and again 2R, R, this is 2R. Now total I have taken 3-bit. Now this is the diagram for the 3-bit DAC. If it is a 4-bit, then we need to add one more R and 2R here. But for easy calculation, now I am explaining the 3-bit. Now if I take 4-bit, then the length will increase. That's why I will try to explain with the 3-bit. So the same process you have to apply for 4-bit also. Now here this is This is a MSB bit, this is a LSB bit. So this is a bit number 2, binary bit number 2, binary bit 1, binary bit 0. Now for this, now here this is the switch. Now we can apply this to either ground. Now this is the ground, and otherwise I'll take ground separately. So this is the ground. Means what? If I wanted to apply logic 0, this switch should go to the ground. Now to this. Now and another one I'm applying to the minus V reference, minus VR, V reference. Some voltage I'm applying here. So now if I wanted to give this as a logic 1, then I have to keep this switch to the minus VR. If I wanted to apply logic 0, then I have to turn this switch to the ground. So like that I can change the binary values. So now 3 bits I have taken means what? So my inputs are from 0, 0, 0 to 1, 1, 1, total 8 bits, total 8 combinations I will get. So for that each, if I put all zeros, then what is my output? If I take only 1, if MSB is 1, then what is my output? If the B bit is 1, then what is my output? If only LSB is 1, then what is my output? If I know the individual bit magnitudes at the output, then by using superposition I can get the remaining combinations also. So this is about the R to R. Now here I have taken the, now one more 2R I have to take, and that I need to give it to the ground. Okay, this is a 2R. This is the final circuit diagram for the 3-bit R to R ladder. Now this is for the 3-bit. So only 3 bits I have taken. Now for that I need to derive the expression for the V out. So V out. Now here I am drawing the table digital inputs and analog output. Analog output. What are digital inputs? So here B0, B1, B2. Now what are the combinations? So total 3 bits are there. So how many combinations we will get? 2 to the power of 3 is equal to 8 combinations we will get. That is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and last all ones. If I get the magnitude for this only B0, if I get the magnitude for B1, and if I get the magnitude for B2, the remaining combination, now here if you see 2 bits are 1, here 2 bits are 1, 2 bits are 1, 3 bits are 1. The remaining I can get by using the superposition theorem. Means if I get this one and this one, then this is nothing but what? Combination of summing of this and this. So like that only if we are going to derive the expression for 3. So that is for this, this and this. And after that you can get the remaining by just simply adding the two combinations of three outputs. Okay, so now here for this what we are going to get? 0 volt. Here the output V0 we are going to get 0. Why? If all are in ground position, so input voltage is nothing but a 0, so thereby output is equal to what we will get? Gain into input voltage. If everything all are connected to the ground means what? Nothing. We are not going to get anything at the output. That's why for all zeros it is 0 only. Now I need to derive the expression for 0, 0, 1. For 0, 0, 1 how to calculate? Now if you see this 0, 0, 1 is nothing but what? Let me derive the expression for this. Now here if this B1 is connected to the reference and the remaining 2 are connected to the ground. So at the time the diagram look like this. Now here B0 is connected to the minus V reference and the remaining all are connected to the ground. So B2 is connected to the ground and B1 is connected to the ground. Now at this time, now I need to calculate the voltage and resistance at this point. Now here, so what is the voltage and to our equivalent resistance at this point? By using the Thevenin's equivalent theorem I have to apply. Now let me apply the Thevenin's equivalent theorem first here. Now if I am applying the Thevenin's equivalent theorem, now here the voltage is minus V reference divided by 2. Why? Because 2R. Now here I am opening. So how to calculate the voltage and how to calculate the Thevenin resistance? To calculate the Thevenin resistance, first ground all the sources. Now here I am grounding the source, then I need to calculate the resistance. If these two are in parallel, then what is the resistance? 2 are in parallel, then I'll get the R is the Thevenin equivalent resistance. Now how to calculate the voltage? Now here the voltage is applied minus B naught VR. So then what is the voltage at this point? Now both the resistors are there, just apply the voltage divider method. Voltage divider, if I apply, both the resistors are same, that's why here I will get half of this voltage, that is nothing but what? Minus VR B naught by 2. So this is a voltage divider method. So 2R and 2R, this is 2R, this is 2R. So here it is grounded and here it is given minus VR, B naught VR. So what is the voltage at this point? Means how we will calculate? Minus VR B naught divided by 2R plus 2R into 2R. Thereby 4R into 2R means what? What you will get? RR will get cancelled and 2 and so you will get totally, this is the voltage. The same phenomena we are going to apply everywhere, okay? Now, up to this point we calculated the voltage and resistance. Now, this is the voltage and this is the resistance. Now, next, this diagram as usual I am drawing. So, this is R, this R here I am drawing and this is the 2R grounded. Again, this is the R and this is the 2R I am grounding. Now, at this point we need to. Now, R and R, it is nothing but what? It is in series and here we will get the 2R. Now again we need to calculate, now up to this point I need to calculate the Thevenin equivalent circuit once again. So for that what I need to do? First ground the supply, then 2R both are in parallel, thereby I will get R is the equivalent resistance. Now here the voltage is what? Minus VR divided by 2 B naught. Now again what is the voltage over here? Again it is a apply voltage divider method. Here it is 2R, it is 2R. Then here how much voltage you will get? Half of this voltage, nothing but what? VR divided by 4 into B naught. Now this is the voltage we are going to get at this point. Now after that what? I have to draw this diagram again. Now R I am drawing, this R I am drawing and this 2R I am drawing once again. Now I need to get here at this point I need to get the equivalent diagram for this one. Now again R and R both are in series means what? This is 2R. This is 2R. Now how to calculate the equivalent resistance? Ground the supply, then this 2R and this 2R comes in parallel. So thereby I will get one resistor, that is R. And what is the voltage at this point? Again apply the voltage divider. Then here we are going to get half of this voltage, that is nothing but B naught VR divided by 8. So this is the final circuit diagram at this point. Now if I redraw this diagram, applied the Thevenin equivalent circuit and finally I got this. So now here what I got? This is the R is the total resistance and the supply is the minus VR B naught by 8. Now if this R and this R both are in series, then I can rewrite this as a 2R. Now what is this? Is nothing but about non-inverting amplifier. Inverting amplifier output is equal to what? Gain. Gain is nothing but what? Feedback resistor by input resistor. 2R by 2R. So here it is minus into minus input voltage minus. So VR by 8 B naught. So minus into minus plus and this gain is 1. So V naught is equal to what I am getting here? VR by 8 into B naught. Now here, so my output voltage is VR by 8 into B naught. If I take reference voltage as a plus, then I will get a minus VR over here. Okay, this is for the first condition. Now coming to the next condition. So now here for this one, if I calculate the same process you have to apply. Now this is R, this is 2R and again this is R, 2R. Now here I am applying this is B1, I am applying V reference over here. Now again this is R and 2R and this is grounded, this is also grounded 2R. Now this is the case. Now for this is what? Only B1 is connected to the ground, remaining 2 are connected to the B1 is connected to the reference, remaining 2 are connected to the ground. Now if I calculate the equivalent resistance, now here R and R are in parallel, then I'll get R. And R is in series with this R, then I'll get a 2R over here. And this 2R and this 2R, if it is in parallel, then I'll get a single resistor over here and this is R and this is R. Now if I calculate the Thevenin's equivalent voltage, then I'll get the voltage here B1 V reference minus B1 V reference divided by 2 I'll get. So now again up to this point, if I try to calculate the Thevenin's equivalent circuit, now I'll get the voltage half of the voltage and the resistance is VR. Same how I calculated for the previous one. Now same you have to calculate the same method. So now here it is minus V reference B1 by 4. Now here R and R both are in series. If I take the equivalent resistance, then 2R. Now if I calculate the V0 is nothing but what? Again gain. So both the resistors are same, so gain is 1 and output is equal to gain into input, that is nothing but what? Minus of minus VR B1 by 4. Minus of minus is plus, so VR B1 by 4. Now for this we will get VR by 4 B1. Again similarly, if you do the same calculations for the resistor, the first one for the MSB bit. Now this is the MSB. I am connecting the B2 to the minus V reference. So now if you do the same Thevenin's equivalent diagram, then you will get the final diagram. You will get here it is a 2R and here the voltage is V reference minus V reference B2 by 2. Here it is B2 by 2. So then you will get the voltage gain is 1 and finally here you are going to get V reference divided by 2 B2. Now in this case just you add this magnitude and this magnitude, then you will get the 3. For 3 what is the formula? VR by 8 B0 plus VR by 4 B1. If all are ones, then so this one we need to calculate. Now here I can give the final output voltage V0 is equal to V reference. If I am taking out, then what I will get? V reference B0 by 2 to the power of 3. So nothing but 80 means what? 2 to the power of 3 plus B1 by 2 to the power of 2 plus B2 by 2 to the power of 1. Now this is the final expression for the 3 bit. If it is a 4 bit, then you will get B0 by 2 to the power of 4 plus B1 by 2 to the power of 3, like that you will get. So this is about the R to R ladder network. So by applying the digital inputs, we will get the equivalent analog signal by using this expression. Thank you.